So this discussion will be on Chapter 3, which is Kinematics in two-dimension. And so dealing in terms of vectors. And so we saw in terms of Chapter 2, we talked about motion in either being in terms of just in the x or in terms of the y. And now we'll be looking in terms of something going off at some other angle. So first off, in terms of vectors and what those are, for a vector, it has two components. It has a magnitude, which is basically how big is it, and then it has a direction. So an example of a vector would be something like this, traveling at 40 meters per second in a northerly direction. So it's a vector. It has magnitude and direction. And so for today we'll be talking about things going off at other angles other than just either straight in the x or straight in the y. Well, in order to do that, we need to talk in terms of some right triangle trigonometry. So if we look in terms of a right triangle, and the angles generally labeled in the capital letters, and angle C is my right angle. And then we have that side A is opposite angle A, side B is opposite angle B, and then side C is opposite angle C. Well, then in regards to a right triangle, there should be at least one equation everybody remembers, and that is the good old Pythagorean theorem, which was A squared plus B squared equals C squared, where A and B are the legs, and C was the hypotenuse. Well, for today then, we're going to get into a little bit of trigonometry. And so if we give this my generic notation for an angle, which is theta, we can look in terms of sine, cosine, and tangent. So sine theta is taken to be the opposite side over the hypotenuse. So relative to this angle, this is the opposite side, and then the longest side is the hypotenuse. The next one will be cosine, and so cosine is adjacent over hypotenuse, which in this case, this is adjacent to my angle, so we get B over C. And then the last one is tangent, and tangent is opposite over adjacent, which in this case will be A over B. And those are my three trig functions, and we will be using those basically throughout the rest of the quarter. So, for example, how does this work? So let's say I now have this. So we go this way, go 350 meters at a 20-degree angle, and I want to know how far in the x direction, there we go, and how far in the y direction. There we go. So I want to find x and y. Well, let's first out by finding x. Here's my angle. This is the adjacent side. This is hypotenuse, and so that is our cosine function. And so we get that the cosine of 20 is going to equal x over 350. And then the opposite of dividing is to multiply, and so we get x is going to be 350 times the cosine of 20. And so then that you will plug in your calculator and get the answer. Now, this is one of the few times where the mode of the calculator does matter, and that my angle here is given in degrees. And so when we do this calculation and we're using trig functions, we got to make sure that the mode matches up. And so seeing this angle is in degrees, your calculator does need to be in degree mode. And when you do that, this will come out to be 329 meters. We can then look in terms of the y part of this. And so this is opposite over hypotenuse, and that'll be sine. So the sine of 20 is y over 350. And again, multiply, we get y, it'll be 350 sine of 20. And that'll come out to be 120 meters. Okay? So we know that in terms of this, if we go 350 meters at a 20-degree angle, we will go 329 meters in the x direction and 120 meters in the y direction. Okay? Well, now what happens if I did the same problem, but given the reverse information? So now we have this. We have my axis, right? And we now know that the person first goes 329 meters this way. Okay. They then go 120 meters in this direction. And what I want to know is, how far is it from here to here, and what is that angle? So I know those two things. Well, this is a right triangle, which means I can find this length by using the good old Pythagorean theorem. And so we have that a squared plus b squared equals c squared. So 329 squared, 120 squared equals c squared. The opposite of squaring a number is to find the square root. And so we end up that c will be the square root of all this. And that'll come out to be basically 350, like we had before. And that'll be me. Well, now I want to know what is the angle for this. Well, here's my angle. Now, relative to the given information, this is opposite, this is adjacent, which is my tangent function. So we get the tangent of theta is going to equal 120 over 329. Well, I don't want to know what theta is. I don't want to know what tan theta is. I want to know what theta is equal to. And so we get that theta will be the inverse tangent of 120 over 329. Okay? So again, on your calculator, if you look on your calculator, you'll find buttons that say sine, cosine, and tangent. And then right above them as a second function will be sine minus 1, cosine minus 1, tangent minus 1. And that's what we use when we want to actually get an angle. And so if we plug this into the calculator, we should find out that this will come out to be basically 20 degrees. And so that information matches what I gave up above in terms of my given problem. Okay. So, in terms of other problems dealing with this stuff, we can look at one like this. So again, let's set our system. Okay. And so we first take off and go 215 meters in this direction. And then at that point, we then take off at a 45-degree angle. So let's put a compass point here. And then from here, we go up at a 45-degree angle, and we go 85 meters in that direction. And I want to know how far in the x did we go total, and how far in the y did we go total. So relative to this point, how far in the x did we go, and then how far in the y did we go. Well, this one is entirely in the x, so I need to add on this part of it. Okay? And so we said this was 45 degrees. Okay? So we need to find the x and y component of this triangle. And so we have that in terms of the x, we get that the cosine of 45 is equal to x over 85, which means x is going to be 85 cosine 45. And you put that in, and that'll come out to be 60.1 for that part. So that'll give us the x part of this. We can also find the y part, and as we did in the previous problem, we'll use sine, and we get the sine of 45 is going to equal y over 85. And so y is going to equal 85 sine 45. And that also comes out to be 60.1. And so we get that. Okay. So that would mean in terms of my problem then, we know that for this one, in the x direction, it went 215 from the first part plus the 60.1 from the second part of the journey, and we get 275.1 in the x. And then the y direction of the journey is just due to that part, and we get 60.1. So you get how far in the x and the y we have traveled. Well, in terms of this chapter then, now that we got a bit on vectors, the chapter deals primarily with projectile motion, right? And describing where the object will be at any given time. And so for that, we'll run through some various scenarios here. And so let's look in terms of this simulation here. And basically we got, in my first scenario, with my object, my projectile is 100 meters above the ground. It's going to have a launch angle of 0 degrees, which means it's just going to go out straight and down. And it has an initial velocity of 31.3 meters per second. So let's look at this. So projectile motion, and this will be scenario 1. Okay. So from this, we got that theta is going to be 0 degrees, okay, launch angle, and the velocity of my projectile was given to be 31.3 meters per second. And I want to find out two things. I want to find out how long is it in the air, so how is the time in the air, and I want to know where does it hit. Well, given that the launch angle is 0 degrees, this 31.3 meters per second is entirely in the x direction. There is no y component to that velocity. Okay. So the first thing we need to know is how long does it take for my object to drop 100 meters. Okay. And so we can use the equation that we used in terms of the first week's lab, also in terms of last week's problems. And we have this equation that y was equal to 1/2 gt squared. So we can solve this equation for t. So multiply by 2. That'll get rid of my fraction. So we get 2y equals gt squared. Opposite of multiplying is to divide. So we get t squared equals 2y over g, and so t will be the square root of 2y over g. And then we can take our numbers, and so t will be the square root of 2 times 100 divided by 9.8. And that'll give us 4.52 seconds. Well, now that we know the time, we can figure out where it hits, because we have our basic equation that x is equal to V times T. So 31.3 times 4.52. And we figure out that the object will hit 141 meters down the road. Okay. So we got our time number 4.52, our distance of 141 meters, and we can check that against our simulation. And so we run this, and we get 141 meters and 4.52 seconds. Okay. So it matches our calculation. So we're going to change our scenario a little bit, and we're going to readjust our angle for this. And so this time, we will change the angle to 45 degrees. And we're going to bring this back down to ground level. Right? So now I know what happened in terms of this scenario. Right? So first off, in terms of my launch angle, you got that if everything being equal, if you want to get maximum distance, you would shoot the projectile at a 45-degree angle. That gives you maximum distance. Right? And then you change that depending on the wind, whether it'll help your shot or not. So if in terms of you're playing golf, and if the wind will help to carry the golf ball for you, then what you want to do is hit the ball at a steeper angle, so greater than 45. That way it gets up in the air and the wind helps to carry the ball for you, give more distance. And then if the wind is blowing in your face and would actually end up blowing the ball back towards you, you want to keep the ball down lower, and so you would hit it off at an angle less than 45 degrees. So let's see what happens in terms of this scenario. And so we'll call this scenario 2. Okay. So again, V naught is 31.3 meters per second. And this times theta is 45 degrees. And we are starting at ground level. So my Y is 0. Okay. Alright, now this time when I fire my projectile, well, you got that part of its velocity will be in the X direction, and part of that velocity will be in the Y direction. And so we get these two equations. We get that the initial velocity in the X direction will be given by V naught cosine theta, and the initial velocity in the Y direction will be given by V naught sine theta. So those are my two equations. So we need to find out what is the X component of this velocity, what's the Y component of this velocity. So we get 31.3 cosine of 45. And so we put that in, and we find out that this will be 22.1 meters per second. We can also do the same thing with the Y component. 31.3 sine 45. And that will also be 22.1 meters per second. So we know what the velocity is in terms of X and Y component. Now, in terms of my projectile and its path, projectile motion, in this case, because the landing position will be the same height as the starting position, and so you got, again, back in terms of this, that it's going to take off, it's going to go like this, and it's going to land, and so the landing point is at the same relative position as the starting point. Right? And that motion will be symmetrical. And so you got that the time up is going to be equal to the time it takes to come down. So time up is going to equal the time down. And the time up is going to be dependent upon this velocity in the y direction. And so we get that time up is going to be given by the initial velocity in the y direction divided by g. Okay. So in this case, we get 22.1 divided by 9.8. And so we get that this time frame, then will be 2.26 seconds. So it'll be 2.2 seconds to go up. It will be 2.2 seconds for this object to come down. And so the total time for this event will be 4.52 seconds. So my total time will be 2.26 seconds up, 2.26 seconds down, so we get 4.52 seconds. Well, we can find out in terms of my projectile, we can find out now where does it hit, how far away does it hit, and how high up does it go. So, in terms of how high up does it go, we get y equals, right? We get y equals y naught, v naught, so yt, 1/2 gt squared. Okay. Y naught is 0. V naught y we got was 22.1. Now the t we're going to use is the time frame for when it hits max height. So I want to know how high up does it go, and so that occurs at 2.26 seconds. And so we get y equals 22.1 times 2.26 minus, plus 1/2. G is a negative, so minus 9.8 times 2.26 squared. Right? So you can either put it as G as minus 9.8, or you could just put the minus sign out here and do minus 1/2, 9 times 2.26 squared. Right? So we plug all that in, and we end up that this will get a maximum height of 25 meters. Okay? Now, where does it hit? Well, the x direction will be given by v times t. Now, gravity has no effect on the velocity in the x direction. Gravity only affects the y direction. So this will be 22.1 times 4.52. And that will give us 100 meters. So we know it's going to hit 100 meters down the road. It goes to a maximum height of 25 meters and is in the air for 4.52 seconds. And so we can test that now against this scenario. And so we run this. We get 4.52 seconds, 100 meters, and given this scale, that is about 25 meters up. So it matches our calculation. So the third scenario we're going to run is now going to be this. Okay? So 100 meters up in the air, still a 45-degree angle, but this time with my projectile, it's going to actually be landing at a lower distance than where it was fired from. So the time up in this case will not be equal to the time down. And so I want to know what happens in terms of this scenario. Okay. So let's call this scenario number 3. So again, V naught is 31.3 meters per second. Theta is 45 degrees. And we start out at 100 meters above the ground. Right? Again, we need to know in terms of my x and y component of my velocity. And so we got V naught x is V naught cosine 45. And we had that number earlier. And we said that that number was 22.1 meters per second. We also need to find the y component of our velocity. And again, we did that earlier. And so this will be 31.3 sine of 45. And that also will be 22.1 meters per second. So, now what happens? Well, time up. Well, we said earlier from the last page that time up is going to be given by V naught y over g. So 22.1 divided by 9.8, and that will be 2.26 seconds. Okay. So it takes 2.26 seconds to get to its highest point, and then from there it's going to drop. Okay. But this time, again, we said this will not be symmetrical because basically my projectile is going over a cliff. So I need to know when it gets 2.26 seconds up to that highest point, how high up is it? Okay. And so we need to find that number. And so for that, we would have this equation, y equals y naught, v naught y t, 1/2 g t squared. And so y naught's 100. So this will be 100. 22.1 times 2.26 plus 1/2 times a minus 9.8 times 2.26 squared. And we plug all that in, we get that this number will come out to be 125 meters at max height. So the time up we got. So now what we need to know is how long does it take for an object to drop 125 meters. And for that, we can go back and use this equation. Because basically when it gets to that highest point, for a brief moment, its velocity in the y direction will be 0. And so we got that it is dropping from rest. And we can solve this equation for t. And we did that earlier, and we said that t was the square root of 2y over g. So this will be the square root of 2 times 125 divided by 9.8. And this will give us a number of 5.05 seconds. So that would mean then that the total time for my projectile to be in the air is going to be the time up plus the time down. So 2.26 plus 5.05, and we get 7.21 seconds is the total time that my projectile is in the air. So now where does it hit? Will be given by the x, which will be the velocity times the time. The x velocity was 22.1 meters per second. It's in the air for 7.31 seconds. So we get that the projectile will land 162 meters away. So we have here again in terms of this scenario, we know it'll be in the air for 7.31 seconds. It'll reach a maximum height of about 125 meters and will hit 162 meters away from my firing position. So we go here and we run this. And we get 7.31 seconds, 161 meters, and given the scale, about 125 meters. And so it matches our calculation. Right? So you go back in terms of the World War, and you had in terms of Rosie the Riveter and the use of females in the labor force. You also had another set of females who basically his job was to figure out these kinds of calculations for the men in the field. So basically in terms of where would various projectiles hit given the various different guns that were used in the war. And so they went through and did all these kinds of calculations and came up with the tables that were then used in the field. Okay. So, in terms of projectile motion, we have another equation we can use, and we'll look at that in terms of this particular problem, and that is, what will be the range of a projectile fired with a muzzle speed and muzzle velocity of 275 meters per second at an angle of 40 degrees. So I know where does it hit in this case. So I'm going to find the range, and so there's one other equation from this chapter, and that is this equation, that the range is given by the initial velocity squared sine of 2 theta over g. Okay. So in terms of this particular problem then, my initial velocity is 275 meters per second, and so we get R is going to be 275 squared. Theta was 40, and so 2 times 40 would give me 80. So this becomes the sine of 80 divided by g, which is 9.8. And you plug all that all in, and this will come out to be basically 7,600 meters. So in terms of this one, we know that it will hit 7,600 meters downrange. And so we got the range of our projectile. And so with that, that will conclude our discussion from Chapter 3. Thank you.